Hi, from Gabriele of Staticalmo, the statistical consulting service that aids your micro, small, medium company or organization to make decisions that agree more with statistics. Today we have a case that deals with financial data about companies. The prospect said we have internal dataset that includes both quantitative and qualitative information from thousands of individual firms for multiple years. They provided a detailed dataset with descriptions, and we have this as dependent variable. Firm applied to bank loans, and we want to understand which firms apply for bank loans. Here we have the description of all the other variables, something that I really advise. It belongs to the good practices. It helps the statistician, and not only to understand how to work and with what to work. They ask first for regression analysis, then a logistic regression, but of course with a 0-1 variable we can just use the logistic regression, and I find this honestly a bit weird. Then he wants, of course, a comparison of models, then a class analysis that I want to do, and then they say they have a budget that goes from $40 to $80 per hour. And that is one of the few cases where a person actually rightly budget a project, at least in Western standards. Let's go into JASP to see what I did. First of all, I did frequency table for the target variable because I wanted to see if we have already a pre-tidied data set, and in that case I would expect 50% for the yes to apply to a loan and a 50% also for no. In this case, no, we have unbalanced classes, and that means that the logistic model of course will suck, because it performs way less when we have around 50% for each label. Then I did the Kendall tau correlations because we don't have quantitative correlations, so we can't use the linear ones of Pearson. Since we have this amount of columns, you understand that running a correlation for 16 columns and over 10,000 rows gives some computational problems. So here you see a subset of correlations, and here another subset of correlation with the significances. We have 9 significant variables out of 16 with the Bayesian correlation. If we did partial Kendall correlations, probably the result would change. At the end I did another part of the correlations, and you see that here we have no significant correlations. Now let's go to do the model, and here it looks a bit messy because we have to go here and select these variables. We select logistic regression, dependent variable is this one, and then we have to go up and say put this here. Then we have this. After putting all the significant variables, we go to see the results. As you can see, we have 2 non-significant variables. We build a confusion matrix, and as I anticipated, we have most of the correct inside the 0 label, not 1, because we have an unbalance 73% of 0 against 26. Nothing new under the sun. Before moving to the extreme gradient boosting model, let's do a second model without the non-significant variables that we find here. I remind you that here we have an accuracy for the rare class of less than 1%. In this second model with all significant variables, you can see that the accuracy for this class of the target variable remains the same. You might wonder why we had non-significant variables here, even though the Bayesian correlations showed significant variables, because as I said, this is not enough to do a performing model, because here we have this method that is Kendall. If we do partial correlations with the Kendall method, most likely we will have variables significant as this second model shows. Now let's go back to the data description and let's see if the model makes sense. We have D2, that means financially autonomous, and we have a positive coefficient. That means that financially autonomous firms are more likely to apply for bank loans. Then we have the larger the company, the more likely their chance to apply for bank loans. And then we have if they deal with the manufacturing, they are less likely to ask for a loan. If they are headed by a woman, they are less likely to ask for a loan. If they had a worsened situation, they are more likely to ask for a loan. With the last one, I don't know what it means honestly. Basically, if this condition is met, they are more likely to apply for a loan. I can say, even though I'm not from the field, that those variables might make some sense, especially this one. This one not so much, and also this one. I wouldn't expect a significant difference by man and woman, but I'm not so informed on this. I feel surprised that those variables do not result significant. One problem I see with this dataset is that we have all variables specified as 0 and 1 except the last. I think that with quantitative variables we could have created more variables that possibly would have improved the model. At this point, who has a IT approach to statistics goes directly to an extreme gradient boosting model, because it can deal better with this situation, but also leads to more overfit. Here, as you can see, we don't have it, we have just a boosting. I decided to go on orange to do the models, because it takes less time than writing code on R, even though I could have checked there the partial correlations for the variables. As you can see here, I put the significant variables we found on JASP. Then I did some data split training and test. Here you can see I did many kind of models. This is the computer scientist way, and especially this kind of model, I think they misuse it because it's too often used. And here we see the results, and they are a little difficult to read. This means area under the curve, the more the better. In this case you see that it is 50%, 60%, but you don't have to get misled by this, because most of this value come from the correctly classified in the zero label. As you can see, all the model have like more than 70%, even 99 in the zero. The problem, as you can see, comes from the 1. Here you have 3, even though we have an extreme gradient boosting model that generally used to overfit a lot. That means very high performance on the train, and on the test it generally goes down. But I want to show that with my surprise, we don't have this model as the best as anticipated before, but this one, the K nearest neighbor, that is generally a model used to do clustering. As you can see here, we have 23% correctly classified. If you go with this other view, you can see the absolute numbers. In the previous view, we could see this with the recall, and still this is not a satisfying result. Is it true that we can still do a lot to improve the model? For example, something that is mentioned here, that means the threshold optimization. Why? if I try to do the prediction of the best model, that is the KNN, you see that in this label, we don't have the probability of the label, but the actual label. So I can't do the distribution of the probability that the model assign to each row of the test data. And from that distribution, I would see the optimal threshold to classify one probability as 0 or 1. I mentioned it also in another video. The default model says if probability major or equal 0.5, then 1, otherwise 0. Nothing prevents me to establish another threshold. For example, 0.2 becomes 1. So of course those are improvable models, and we would see that at one point this will improve greatly at the price, of course, of more of this category. That means false positives. As you understand, this program Orange is fast, but of course it lacks some depth that the statistician needs in order to do a model that works. If you want to reduce a rare event connected to your company that annoys you, of course, thanks to statistics, as you just saw, and to modeling, we can do that. You can contact me on the contact page of www.staticalmo.com, and we will find an agreement. I greet you. See you the next time.